Hello, everybody. We are here to do the 2015 Calculus A, B, and BC question number 3. This has been a fiasco. I recorded all these yesterday but my audio was turned off, and then I tried to overlay it in an editing program, and that got all messed up. So, starting from scratch. So here we go. So for AB students this year, you won't be required to do the integration part of these type of problems, but you still need to understand the concept of position, velocity, and acceleration. So let's take a look. We have a Johanna jogging for 40 minutes. And so the velocity is differentiable v. And let's see what they want. We want to estimate the derivative of v at 16. So I'm going to remind some of you, I've shown you this many times. So I'm going to plot these points. It's not actually these points. I'm just doing 3 points that randomly. And so there's a function that goes through these points. So these are just 3 sample points. And actually, I just want to do 2 of these points if I get rid of that. Yeah. So suppose we plotted 2 of those points, and they want us to approximate the derivative. I'll make up some numbers here. They want it at 16. So imagine this was 12 and this was 20. So they want to approximate the derivative at 16, which would be the slope of that line. So I will do a red line. They want us to approximate the slope of the tangent line, aka the derivative at 16. So how do we do that when we don't even have a function? I'm hoping you've seen this so many times, it's ingrained in your brain. We're going to find the slope between 2 random points around it. So we're going to pick 2 points around the point where we're trying to find the slope, and just find the slope between those points, also known as the average rate of change, also known as the slope of the secant line. And I think you all can handle that. So what is the slope? So what are we doing? We're approximating the derivative of v at 16, and that's approximately equal to v at 20 minus v at 12, because those are the points around it, over 20 minus 12. So we have 240 minus 200 over 20 minus 12. Leave it like that. Don't simplify it. You don't need to. Just leave it. Part B. So using correct units, explain the meaning of this integral and approximate this value using Wright-Riemann sum. So let's do the first part. We're going to interpret the meaning. So let me draw another example for you so you can see kind of what's going on. Suppose we have a velocity graph. I will do it in green. And this will be velocity and time. So what's happening? Here the velocity is negative. That means the person is moving to the left. Over here, the velocity is positive. They're moving to the right. Get you more stuff here. So say the area of this was 15, and the area of the piece below was 5. And let's call that A and that B. So if you integrate from 0 to B, you'd get the net area of 10. Because the person moved, turn my pointer on. Let's see if I can get it to come on. There it is. So you move 15 spaces to the right, 5 spaces to the left. So the change in position is 10. But that's not the total distance traveled. If you want the total distance, you need to make this 5, which is negative, positive. You do that by integrating the absolute value of v of t. Now you get the total distance traveled. So just realize when you integrate a velocity, any negative velocities, that will be subtracted. That distance will be subtracted. So this is the total distance Johanna traveled. So we can write that out. The integral from 0 to 40 of the absolute value represents the total distance Johanna jogs. We should get units. I need to put units here. So let me explain the units. So you have to understand integrals are adding up a bunch of stuff. That's all it's doing. So that doesn't change units. So the units of velocity are meters per minute, and the units for time are minutes, or is minutes. Units are minutes. So you cancel those out, and you're left with meters. So that's the units they're asking for. So be careful, read the question using correct units. Jogs in miles during t, that's kind of awkward English, equals 0 to t equals 40 minutes. That's it. So total distance, and in a context, you have to talk about Johanna jogging. That's what it means in the context of the problem. So that's first part of B. The second part, we need to use right Riemanns to approximate this. So let's do this. So we're doing, I'll circle each subinterval. Here's between the first two. The right-hand side clearly is the 12 seconds or minutes. So it's going to be the velocity at 12, absolute value, and the change in time is 12. My next interval will be these two. And the right-hand side of that is 20. So it's v of 20 times the width is 8. Now you could put 20 minus 12 if you wish and not simplify that. The next interval is this one, and 24 is the right-hand side clearly. Oh, I forgot the absolute value on the previous one. Some of you are probably screaming at me, even though I couldn't hear you. V of 24. And the width is going to be 4. And the last interval is going to be these two, or last subsection. So the right-hand side is 40, and the width is 16. Now we need to replace those values, and that should be a squiggly there because we're doing an approximation. So it's going to be 200 times 12, 240 times 8, 220 times 4, and the last one, 150 times 16. All right, that's it. That part did not ask for units. If you want to put units, you could put meters. But that is part A and B. All right, let's look at part C. We have a guy named Bob. Hello, Bob. Hello. Bob is riding his bicycle along the path for 10 minutes. Bob's velocity, so here's Bob's velocity. That's not his position. Be careful, velocity. And you want to know his acceleration. How do you find his acceleration? So acceleration at 5 will be the derivative of the velocity at 5. Oh no, I need the derivative of b. So side work, b of t is 3t squared minus 12t. So then it'd be 3 times 5 squared minus 12 times 5. Finished. Don't simplify that. You are done. You are completed. Please do not proceed any further. That would be foolish. And then part D. Based on the model in B, based on the model B in part C, find the average velocity. Okay, for those of you who don't have this down, you need to understand average velocity. It's different from average rate of change. So do not confuse the two. Average rate of change, it's a rate of change. So it's the rate, the change in the y over the change in x, or whatever your variables are. Average velocity comes from the mean value theorem from integration. But here is how it goes. Average velocity, you would integrate the velocity and divide by the width. So that, if you want to refresh yourself on that, you can look for some videos online, look at the notes. Or if you text me or email me or get a message to me, I could make a little video reminding you of where that comes from so you understand the concept. But let's work this out. T cubed. All right. All over 10. Don't forget the 10. So antiderivatives, t fourth over 4. 6t cubed over 3 minus 300t. That's from 0 to 10, all over 10. Now plug in 10 and plug in 0. Do not simplify, please. I beg of you, do not. Even at 6 over 3, I wouldn't simplify that. You might do something dumb. All right. Now, when you plug in 0 for all the t's, you're going to get 0. So that's just that. That's your answer. Plain and simply, that's it. You don't have to do anything to that. Don't be a fool. Don't change it to 350. Now, let's read the question. Make sure we answered it. Find Bob's average velocity. We don't need units. We are done. There it is. That's it for this one.